Robot Talk is the podcast that sits down with robot enthusiasts from around the world and asks them the questions you always wanted answered. Like, is that a bat or a robot? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and this week's episode is all about bioinspired robotics, and specifically, what we can learn from bats to make robots that are able to autonomously navigate through complex natural environments. But first, I'd like to remind you about our competition to win your very own Robot Talk t-shirt. Our winner for December was Karen Donaldson, and we'll be selecting another lucky winner at the end of January. For the new year, we've decided to mix things up a bit. We're still running our competition, and we'll still be giving away one t-shirt each month for the rest of the season. But from now on, you can enter the competition by signing up to our newsletter and reposting our competition post on social media. For more information about the competition and how to enter, check out robottalk.org. So, with all that said, I'm excited to introduce this week's guest. I recently had a fascinating chat with Rolf Mueller from Virginia Tech, all about biomimicry, flapping wing flight, sensing, and artificial intelligence. This week, I'm chatting to Rolf Mueller, a professor of mechanical engineering at Virginia Tech, working on bioinspired robotics and autonomy in natural environments. Hi, Rolf. Great to have you on the podcast.
Yeah, thank you for having me.
So I first came across your work because of a flapping wing biomimetic bat robot that you've worked on as part of a collaboration with the University of Brunei. And it really caught my eye, in part because it's quite unusual to see flying robots that actually have wings that flap rather than like rotors, for example. So why did you want to create a flapping wing robot, and what engineering challenges did this project represent?
If you take a clue from the bats, there's a lot of advantages to be gained from using flapping flight as a principle. Right? It is much more maneuverable than rotors. It can be much more energy efficient, and it can be completely silent. Right? If you have ever seen a drone or heard a drone flying overhead, a rotary drone, you know how much noise they make.
Yeah.
And if you imagine now we are going to put all our parcels on drones, imagine what kind of noise that would be.
Yeah.
So flapping flight has a lot of advantages there. There's also numerous challenges, right? It's a really complicated flying machine. So bats have about 20 discrete degrees of freedom per wing, so 20 joints, plus the wing membranes have muscles in them. So how to replicate that, that's still an open question.
Yeah, I mean, I've seen some videos of what you've got so far, and it's pretty impressive.
Thank you.
So are you trying to directly mimic every aspect that you just described, or are you kind of using the bat wing as a starting point and then, you know, making some concessions based on engineering principles?
So our hope is not having to replicate all 20 degrees of freedom. And so some of our ongoing research is directed at finding out what is it that we actually have to replicate. So we are, over the past summer, we have collected quite a bit of data on bats making flight maneuvers. And the hope is that we can analyze that data and see what are the essentials and then make choices and say, okay, we can maybe replicate that's energy efficiency or whatever it is to a certain level that will be good enough for us, and there will be an advantageous trade-off point where we can say, okay, the complexity is still within range, what we can do, and then the benefits are already are good enough, and then maybe this is then the right point for us to stop.
Okay.
But since we haven't done the research yet, I cannot tell you where that will be. But it could be that we really have to have 18 out of 20 degrees, and then we are not going to save that much, or it could very well be then maybe we are getting away with 4 or 5 degrees of freedom and can already get to 95% of what the bat achieves, and then we would probably say that that is enough for us.
Sure. And as well as mimicking the flight abilities of bats, you've been working on biomimetic sonar systems that allow the robotic bat to sense the world around it like real bats do. Now, at a basic level, sonar is obviously a technology humans have had for a while. So can you talk a bit about what's so special about the sensory system of bats and why that's difficult to replicate in robots?
Now, it is true that sonar technology has been around for a bit more than 100 years. That still makes it a lot younger than camera technology, right, which has been around for many 100 years.
Yeah.
And if you look at what we have in terms of technical sonar and what BET do, they actually is beyond the very basic physical principle, right, that you emit a sound pulse and you receive an echo. Beyond that, I have the impression that they don't have much in common. So engineers over the last 100 years, right, they have treated sonar essentially as a poor man's vision, right? So you want to recreate what vision does, but unfortunately you're hamstrung by much larger wavelengths. And I think it's maybe a bit too harsh to say the last 100 years have been wasted. That's not true, right? They're in sonar technology, but there is some things that are really useful, right? So if you want to do seafloor mapping, and you can do that with sonar and create an image, a 3D image of the seafloor, and that's definitely useful. But I think the efforts are really nowhere where they should have been, and the bets show us that you can do amazing things with sonar without all the complications that you have in technical sonar. So I think that what I'm trying to do with my research is I'm trying actually to take a very different approach and how we look at that sense.
So yeah, I mean, I guess bats can sense tiny insects amongst very complex forest environments, which is pretty impressive.
Yeah, that's exactly the skill that we are interested in. Should maybe for some context say that there's about 1,400 species of bat in the world, and they have very different habitats that they live in and food that they pursue. But there is indeed a group of bats, and it's not a few, where there's several hundred species that have this ability to really go and pursue their food in dense vegetation, right? And so they have an amazing mobility, right? They're like little fighter pilots, only that they are flying in dense vegetation, right? And then they can all do that without using their eyes, right? So it's like you take Maverick and you let him fly the fighter jet in a dense jungle and then cover his eyes. And that's
Yeah.
the kind of skill that we are talking here that the bats have and that we would like to replicate.
I saw a video that you were in where you were talking about the bat's ears and how they play an important role in this kind of sonar sensing capability. Can you explain that a little bit?
Yeah, so bats have this kind of gothic facial looks right on them with the
Yeah.
big, really strangely shaped ears. And these ears, they really affect the waves that come in. There's also for the bats with the sophisticated sonar, when they emit the sound comes out of the nostrils, and there's like a little megaphone. It's called a nose leaf around these nostrils. And again, that has very unusual shapes. And these are all devices for shaping the emitted and received sounds. And so I think how to think about that overall is that the bat is offloading transformation, signal processing that we would, as engineers, we would do it digitally in the bat. If the equivalent would be in the brain, and maybe they're lazy thinkers and they offload that into the physical domain, which is a clever thing because it makes them get away with very small brains. But so typical bat brain, again, it depends on the species, is less than 1 gram of brain mass. Right? So, and that probably corresponds to just a few million neurons. Right? So this excuse to say we cannot do what the bats are doing because our computers are not powerful enough. That is definitely not the argument. If we cannot do what bats are doing, it doesn't mean that our computers are not powerful enough. It means that we are not smart enough to understand what the bat is doing. And I believe that the physical domain, this joint work, right, that you do some of your stuff just with the acoustics, and you do other stuff in your brain, that is part of the secret here.
Yeah, I've talked to a couple of guests in the past about this idea of morphological computation. I guess this is an
Mm-hmm.
example of that.
Mm-hmm. Yeah, I would say so.
So, will your ultimate biomimetic bat robot have, some of these features? Maybe, soft ears or some kind of adaptions of the nose.
Yes, at the moment they do, right? So that is for our current work. We use silicon rubber to make ears, to make nose leaves. Maybe at this point I should also mention that it's even more complicated in that these structures are malleable, right? And so a bat has 20 muscles approximately on each ear.
Wow.
And they make the ear change while the sound is coming in, right? So they make big deformations, right? Ear shape about 1/4 of the height of the ear, they deform it by that much. And that happens in about 1/10 of a second, right? The human blink of an eye, I've read in the medical textbook, is 3/10 of a second. So that means 3 times as fast as you can blink your eye, the bat can change the shape of its ears. And that does very interesting transformations to the signal. For example, we have done the math, what happens there, and we have come to the conclusion that these ear motions are fast enough to make Doppler shifts, put them onto the echo, right? So if the echo comes in, it hits the outer ear is moving, it compresses the waveform if it moves into the sound, or dilates the waveform if it moves away from the sound. So you get positive and negative Doppler shifts on the signal that goes into the ear, and they are actually considerable. They are hundreds of hertz, so it's not small fries. And that's some really interesting principle that no technical sonar uses, and that we have actually been able in a robot to exploit to tell direction of a sound with a very high accuracy. And there might be other more sophisticated applications for that.
That's amazing. Yeah.
Yeah.
So we have an audience question submitted by Maybe My Monkeys on Mastodon, who says, how do you determine how much sensing is required? As an example, human fingertips have more sensory density than human feet.
Yeah, it's a super interesting question. And what I think the bets are telling us is that you can get away with very little sensing, right? If you look at what the engineers are doing, right, when they try to make autonomous systems, say autonomous cars or off-road or drones, right, that are supposed to go into environments where a lot of different things can happen, where things can be complicated. The idea is have a lot of sensing, have really high data rates, right? So I've checked the other day, I checked the spec sheet for a LiDAR, and I think it was 13 megabytes per second was the data rate just of this one LiDAR sensors. So then I have done a back of the envelope calculation, what our bets, what I think their maximum data rate would be, and very conservatively, so I mean very high estimate, a very high estimate would be 100 kilobyte per second is the data stream that goes into their ear. And that is just really, if you sample everything, the raw waveforms, and represent it by a sequence of amplitude values, the bat's brain, the hearing nerve, does something much more clever, right? Just representing it by a couple of spikes, right? Little bursts of activity of the nerve cells. So it is probably even much less. So that is something that I would like to learn from bets, right? How can we do things on low data rates, on small data, right? So in engineering, I think it's a bit of a procrastination tactic, so that you say, okay, the world around me is complex. Let me digitize it all. And then somewhere, I don't know, I have terabytes of data on my hard drive, and I can be sure the information that I need is somewhere in there. But you have still just postponed the challenge, right, of pulling it out of that data. And the bets, they don't suffer from that kind of procrastination syndrome. They just attack that heads on. They start processing the signal in the physical domain with their ears, and then have just a small data stream where the important information is obviously encoded in a very effective manner. And then they use a few million neurons to pull it out and take action. And I think if we want to be autonomous have a drone, a robot that is autonomous in the real world, that can do that with low power consumption, with low latencies, but you want to be quick, right? If you're flying through the vegetation, you want to make these moves that the bats are making. You cannot think about each move for 5 minutes, right? You have
Yeah.
to really make the turn immediately, and that means you have to have very low latency, and that you can only do if your data rates are also low. And I think that's what we can learn from the bats.
Yeah, I guess this comes back to what you were saying before about bats having relatively small brains and kind of
Mm,
doing as much of that processing before the information gets to the brain.
mm.
So the final piece of the puzzle here is creating a bat robot that can navigate and operate autonomously in complex natural environments. And to do that, you've been applying an artificial intelligence method called deep learning to this problem. Can you tell me a bit about that?
Yeah, so the goal here has been to be able to pull information that we need for navigating in the forest, say, directly from the echoes. And so I think that was when we discussed the history of Sonar a little bit earlier in the conversation. The idea has traditionally been that you want to first make a digital model of your environment. And the same is true for LiDAR. Right? So the idea is, yeah, I'm in a forest, I want to navigate. So either I use a sonar array, or better, I use a LiDAR, and I create a digital model of the world that surrounds me. And then I can plan my motions in that digital model of the world. And that's how I navigate. And so our approach was to say, okay, the information is somewhere in those echoes. Can we use deep learning to pull that out immediately without making a digital model of the environment? But because you have very specific questions that you need to answer, right? Am I going to bump into things? Is there a passageway in front of me? Where am I? Can I recognize the location where I am, right? And these are the questions, right? And so we said, okay, no procrastination, no detours. We try to use deep learning to answer these questions directly. And deep learning has now been around for a while. There has been a lot of hype about it. But I do believe that it really has pushed the envelope when it comes to pulling patterns out of data. It is really a lot better than its predecessor technologies. And so I felt when that came sort of into the mainstream and was showing all this promise, I was saying, okay, we need to take another look at those echoes, right? And the echoes are complicated, right? So if you imagine you are in the forest and you emit an ultrasonic wave, it travels like a sphere from your mouth. And then in the forest, right, there's all those leaves, and each leaf is like a little specular reflector, and it makes a little echolet, right? And then if you have a few hundred leaves around you, or I don't know, it could be 1,000, but then you get that many little echolets that travel back to your ear,
Yeah.
and they all superimpose on each other, right? And so you get an echo that is made up of contributions from all these reflecting facets, but there are so many of them that there is virtually no chance of resolving that, of looking at the echo and say, oh yeah, here's a little piece that came from this leaf, and here's a piece that came from that leaf. You have a few milliseconds worth of sound. There's 1,000 echoes in
Yeah.
there. Right? It's just like if I read you some number and say, yeah, that number is the sum of 100 or 1,000 different numbers. Tell me what these 1,000 numbers are, right? And I think if you let the numbers be positive and negative, that there's no way you can do that. And the same thing is true here. So we said, okay, forget about that. We don't want to tease all that apart. We just look at all the sonar engineers call these echoes clutter echoes, right? So we look at the clutter and say, can we pull this stuff directly out? And so we had some really nice successes. For example, telling that there was a passageway in front of us by just processing the clutter echoes, or telling where we are in the forest, right? So we have a little nice, diverse patch of forest here on our university campus, and we were able to tell our location based on 15 milliseconds of ultrasound, right? So 1/60th of a second of an ultrasonic recording. A deep neural network was able to pull out our location with a precision of about 6 meters. We could actually tell
Wow.
where we are. And I think that we use as reference, we use the GPS, and the GPS under foliage, a cheap recreation grade GPS under foliage, gives you about 6 meter resolution. So I'm not even sure what we saw there. What limits us? Was it the sonar or was it the GPS reference? So I've just splurged out some money to buy a better GPS and use a better approach there. And today is data acquisition day. So I think we'll soon find out if we can even be better, if where the limit of the sonar is. So it could very well be that we are better than 6 meters. But I think if you want to navigate in the forest and you can tell with 6 meter resolution where you are, that should not hold you back, right? That could be good enough. And again, you can just do it by running a few milliseconds of sound through a deep neural network. And the same thing for finding those passageways. In the passageway situation, we were even more successful in that we could use transparent AI to see where those features come from, what the network is paying attention to. So we were not stuck at the black box level, and we were then able to make more of a signal processing model that mimics the brain. So all the computational effort that has to go into a deep neural network, we didn't have to do that anymore. So I have a lot of hope there that it will be possible to pull the information that we need to navigate straight out of the echoes and then represent them in a way that needs very little power, very little computation, and then just do it at an instant, just like the bats do.
Yeah, that's really cool. I feel I should mention now for listeners who might not be familiar, and forgive me for my probably overly basic description here, but deep learning basically involves training a neural network, so a representation of how the brain works on a load of training data, and then it picks out patterns in that and kind of learns how to process it.
Yes, that is correct. And I think we might have something to learn from bats there as well, right? Because if you look at how we are doing this at the moment, it's actually very inefficient, right? So what people do is they accumulate huge sets of data, right? So there's a database of images that people use for training network classifiers on images, right? And I think it's now more than 20 million images. Right? And so if you look at bats, right, they mature very quickly. Right? They are made to bat babies, I think, 6 weeks or so. They are weaned from their mother and they go on their own way. Right?
Okay.
And then they are active, as you know, bats are typically active in the night, right? But it's not that they have 8-hour shifts, right? Typically bats, right, they come out and they fly around a little bit and then they take a break and then they fly out a little bit more, right? So they're not typically not the hardest working ones. So you're talking every night, really just a couple of hours at best of echoes, coming a few echoes per second. So if you add all that up, you come to a very small number. Still a lot, right? But pretty small numbers of echoes, and that covers everything, right? It's not just one task, right? It is navigation, finding food, the whole range of things that the bat has to learn. So I think what these animals are able is they're able to learn on small data. And with the deep learning at the moment, we cannot do it, or we are not quite as good as they are. So I think that's also worth looking into. Can we actually have a different approach to learning that is based more on small data?
Yeah, that's really interesting. I imagine that would be a development a lot of other industries would be interested in as well.
Mhm.
So before we finish up, you're creating this flapping wing robot that can sense the world around it, that can do all this amazing processing. What applications do you see for this technology?
I think there are quite a few. Right. So, I mean, I don't know where most of your listeners spend their day. I spend it in an office. So, and people like me, right, on a typical day, I think, what do I need for living, right? I need a computer, a screen, a keyboard, an internet connection, coffee machine, right?
Yeah.
And if that's what I have, then all my basic necessities for life are met. But if you look at what's really going on, right, what humanity needs, food production, renewable resources, ecosystems that can actually maintain life on Earth, right? These are all challenges that happen somewhere outdoors, right? They are not happening in offices. So we cannot save the world in offices. We have to do things in the real world, right? So we have to make our agriculture more efficient and using less noxious chemicals, right? We have to keep our ecosystem healthy, get the garbage that has been strewn around in them out again, all these things. These are all outdoor real world tasks and they are humongous tasks. So
Yeah.
somehow we have to get automation to them. But automation has had a really big impact. Right? If you look over the last couple of decades, what has happened to manufacturing, for example, big changes due to automation, warehousing, right? But what these areas, right, where automation has been really successful, what they have in common is that you have a highly controlled environment, right? So you can set up the manufacturing line so that the robots can do what they are supposed to do. Right? But for these outdoor tasks that we have in agriculture, in environmental surveillance, cleanup, forestry, right? All these areas, forest fire, wildfire, right? Big area, right? That we really need to pay attention to. Um, uh, we don't have that much automation or practically nothing there yet. And I think we would need those. And so I hope that our technologies, mobility, sensing, the combination thereof, that would eventually give us systems, right, that can do things by themselves outdoors and help us address those challenges. Say, how can we make agriculture more precise? How can we collect garbage? How can we monitor our ecosystems better? How can we monitor for forest fires? These kind of things that they will eventually have an impact on those things.
Mm-hmm. It's a really interesting and exciting area of research. So I will be watching and keeping track of this project to see how it progresses.
Oh, wonderful.
Rolf, it's been great speaking to you today. I've been talking to Rolf Mueller, a professor of mechanical engineering at Virginia Tech. Thanks, Rolf.
Yeah, thank you very much.
Thanks for listening. If you enjoy Robot Talk, please do share the podcast, subscribe, and leave a review to let us know what you think. And make sure you check out our social media channels to see a photo of a biomimetic Sonar robot that Rolf has worked on. Next week, I'll be speaking to Elizabeth Sklar from the University of Lincoln, all about agricultural robotics, human-robot teams, and sustainability. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk is brought to you by the Hamlin Centre, Imperial College London.